The next compound operator to look at is join, which is one of the most common tasks we do in relational databases because it allows us to put together data from multiple tables. You'll find that join, or at least algorithms that essentially compute join, occurs all over the place in computer science because it's very common to have two different collections of data and need to connect things between them. Now, joins are actually compound operators in the algebra, like intersection. And as you may recall, the join can be defined as a cross product followed by some selection over a predicate theta. Joins come in the relational algebra in a few flavors that are sort of hierarchical. So the most general case is the theta join, which is just a cross product followed by a selection on any logical expression theta. More specifically, there's a class of theta joins called equijoins, where theta is a conjunction of equalities. That is, it's a bunch of equals predicates combined with and. And then a special case of the equijoin is the natural join, which is an equijoin where the conjunctions are on predicates that match up columns that have the same names across both tables. Now, for all this, we're going to need to learn a good join algorithm, and particularly one that's better than taking a cross product followed by a selection, because as we know, just enumerating the output of the cross product is very expensive. So we're going to learn good join algorithms soon. In the meantime, this is one of the reasons why join is an operator, is because we want to call it out as a special thing that we need to implement carefully. So let's look at a very basic theta join example where our tables are the reservations table R1 and the sailors table S1, and we're joining them on SID. So we're finding reservations and the sailors associated with them. So this is pretty straightforward. We've seen something like this before. And when you combine things by SID, you end up with the relation on the right with the tuples combined together. Note that the output relation has two columns named SID. That's a problem. So we're going to need to use a rename operator to change the names of position 1 and position 4 in this table to something unique. Here's a more interesting theta join example, or maybe just a more complicated one. Here we're taking a very arbitrary theta, which is field 4 is less than field 8. And the table we're joining is S1 being joined with itself. So this is called a self-join. And the idea is that we're going to find pairs of sailors where for the first sailor, their age is less than the age of the second sailor. In essence, we're finding all the senior sailors for each sailor. So remember, our S1 instance is up on the right. And when we look at the cross product down below, we can now filter it by F4 being less than F8. And we get something like this. Right? We rule out all of the things where F4 is not less than F8, leaving us with just 3 rows that qualify, and that's the answer to our query. Right? Note that the result schema of this query, this self-join, is the same as that of the cross product. Right? It's just all the columns are repeated. So here we certainly need a rename to rename all 4 columns, at least. So the next thing we might want to look at after we've looked at equijoins is the natural join, which is a special case of the equijoin. So let's do that next. Natural join is a special case of equijoin in which there's an implicit theta, and it says that the equalities are specified for all matching fields as a conjunction of equalities. Also, at the end of the join, we project away any duplicate fields and keep only one copy of each distinct column. So to reiterate, we're going to compute the cross product, R cross S in this example. We're going to select the rows where fields appearing in both relations have equal values, and then we're going to project onto the set of all unique fields. So here's an example. We're joining reservations and sailors, but this time it's a natural join. So you can look to see what are the column names that are shared between reservations and sailors, and the answer is just SID. So essentially it's an equijoin on SID. But after we're done, we're going to project away the second SID field and leave ourselves with only one. So there's the SIDs that match. Those are the tuples that don't fit the predicate. And then in the result, we only have one copy of SID. Natural joins are pretty common for these sort of foreign key joins like we saw here, where you have a key of one table, SID is the key of sailor, and you have a reference to that key, a foreign key in the other table. We had SIDs and reserves. And when we're done, we don't really need both copies of that key. The key was just there to link up the two tables.